the fifth module in our astrodynamic series called Earth Station Look Angles. And this lecture is really about answering one question that is near and dear to the heart of any electrical engineer working in the satellite field. And that is, if I am an observer on Earth and I want to communicate with a satellite, where do I point the antenna? At what time of day and at what point is the satellite in an orbit, and how do I actually point an antenna to it to actually get the signal? Many of these space links, as we've seen in the early parts of this class, satellite links are unique among the links that we use in day-to-day life because they have to overcome thousands of kilometers of path loss in order to get to your mobile station or your Earth station on the surface of the Earth. So how do we overcome that? Well, one of the ways that we're going to learn when we get into antennas and propagation is you got to make a really big dish. Because a really big dish has a lot of directivity. It can focus power and receive efficiently from a particular direction. But it also has a pencil-thin beam, which is good because when you dial it into a particular satellite up in the sky and point it, that means you'll get that satellite with a lot of gain, and you'll exclude everything else. Everything else will have a significant amount of attenuation, even other satellites that are using the exact same bands. So this is how you reuse frequency in space when you don't have the luxury of the cellular network of having building and trees doing all the hard work for you, blocking signals and filtering out from other regions of the cityscape. So we use directional dishes quite a lot in satellite communications. The downside is that you have to point them because they only have high gain for maybe a plus or minus a few degrees of beam width in most applications. And so you got to figure out where to point them. You got to figure out where to hammer that direct TV dish into the ground and what angle to put it at in order to get this TV signal as the simplest application for that. Okay. So that's the question that we're answering today. And let's answer it by starting off with the typical geometry of the problem. And this is going to introduce some really important jargon that we're going to use for the rest of the class. Here's the Earth. Here's the center. The point where you are observing something, a communication from the satellite, we call that the Earth station, often abbreviating it as ES in this class. And then you, of course, have the satellite in space itself. And if you draw a line from the center of the Earth to where the satellite is, the place where that intersects the Earth has a special name as well. That's called the satellite subpoint. We'll abbreviate that SSP. And if you were standing on the satellite subpoint, the satellite would essentially be directly overhead. We call directly overhead zenith, this direction. And then looking backwards down to Earth, we call this nadir. And the key parameters for figuring out look angles are basically, first of all, the fixed constant that is the radius of the Earth, the radius of the satellite, that is the distance from the center of the Earth to the satellite spacecraft, and, of course, the longitudes and the latitudes of both the Earth station and the satellite subpoint. Now, as a quick refresher, You probably all know this, but I'll put it on the board so you have it in your notes. We use longitudes and latitudes to denote satellite subpoints and Earth stations. We're going to give numerical values to these. Longitude, 0 degrees, is, of course, where? Greenwich, England, which is kind of lined with London. But I think Greenwich is the official demarcation. Exactly. If you have positive values, you are moving east of Greenwich. And if you have negative values, you're moving west of Greenwich. So keep in mind, because there's a 2 pi repetition period to describing longitudes, you may get multiple longitudes for the same point. You could say, oh, this point is at 270 degrees longitude. I mean, you start at Greenwich, you move to 70 degrees east. Well, some people prefer to use negative 90 to denote that. That's negative 90 degrees. And some people, instead of using positives or negatives, they'll use east or west. They'll say 90 degrees west as opposed to 270 degrees east. It all comes out in the wash. Just recognize the different conventions out there. If you see a west next to the degree marker for longitude, when you put it in the formulas, take the W off and put a negative sign in front of it, and it works fine. If you want to add 360 degrees, I think all the formulas that I give you are basically going to be okay to add 360 degrees to, and everything will kind of come out modulus 2 pi when you do the calculation. So that's longitude. And latitude, of course, 0 is the equator. And if we're using raw numerical values, again, you can just use latitude north or south. But in our formulas, everything's going to be plus or minus. So greater than 0 degrees is in the northern hemisphere, and less than 0 degrees is in the southern hemisphere. And if you're wondering, the electrical engineering building, which is not the building where this class is, but it's the building where some of you spend a lot of time. So we'll go ahead and use it as, it kind of is convenient center of Georgia Tech campus. So let's call this the center of Georgia Tech campus, both geographically and in importance, right? No, I'm just kidding. Are the aerospace guys here? Okay. I was just kidding. Not really. No, I'm just kidding. 33.7758 degrees latitude and negative 84.39738 degrees longitude. I'll work an example, and we'll need this number a little bit later, so keep it in your notes. It's always good to know where your school lies anyway. Okay. Now, let's do some honest-to-goodness geometry here with a little more rigor. So if this were a two-dimensional problem, it would actually be pretty easy. So let me draw the two-dimensional problem. We'll solve it with a really simple formula. And then we'll go into 3 dimensions where you actually have to use all the satellite subpoint and the Earth station latitudes and longitudes. That is a tricky problem. Take good notes because it's not in your book. I think the elevation calculation, ultimately what we're after is azimuth and elevation. They contain an elevation calculation, but I don't think they have the azimuth calculation included. And there's some nuances that they don't talk about either. So this may seem like simple geometry, but it actually gets very hairy. So pay attention. Here's our problem. The Earth, radius of the Earth. What is the radius of the Earth? Here's a nice precise value down to the kilometer. 6,378 kilometers. That's about mean Earth radius. We said earlier that the Earth is an oblate spheroid. It's by depending on where you go on the Earth, it could be a few hundreds of meters off. And let's see. Radius of the Earth. Here's our Earth station. Here's our satellite subpoint. Here's our radius of the satellite. Here's our satellite subpoint. Here's our satellite. The centroid of the Earth station, and the satellite make a convenient triangle. And if you can imagine, what is it that we're trying to guess in this two-dimensional problem? Well, in this 2D problem, what we really want is elevation. If I'm an observer standing there on the surface of the Earth, the tangent line that I just drew, the dotted line, is sort of like, that would be what a plane that is tangent to the surface of the Earth at where you're standing would bisect this diagram, would kind of split it, come out of the board, and shear it tangent to the surface of the Earth. And that would represent the upper hemisphere that is actually visible from an observer on the Earth. In other words, if this satellite were to drop below this dotted line, it would no longer be visible, right? And this essentially is 0 degrees of elevation. 0 degrees of elevation is right along the horizon. We're going to measure elevation in this class as a function of degrees away from that horizon line. Now, keep in mind, that's different than the mathematicians, how they taught you to measure elevation, and the electrical engineers that taught your EMAG class. They're teaching you elevation from the z-axis. This is 0 degrees, and then you go down this way to 90 and 180, etc. So just recognize that a lot of the formulas that you'll see for elevation in your math textbooks, you got to massage them a little bit to make it into a look angle. Okay, so this is the angle that we're after. E, we'll call it E little l, L. Okay. So to figure this out, this is actually very simple. I won't derive it on the board because it takes too long, and I'll probably do it at home. But it's basically the law of sines and the law of cosines. You remember those from your trigonometry days? And so the cosine of that elevation angle is equal to, okay, in order to figure this out, I need to figure out what this angle is, gamma, the subtending angle between the Earth station, the center of the Earth, and the satellite subpoint, the angle formed by those two line segments. And if I have that, then I take the sine of that gamma, and I divide it by the square root of 1 plus RE over RS squared minus 2RE over RS cosine gamma. So if I know this angle, I know the radius of the Earth and the radius of my satellite, I'm in good shape. I can actually calculate the elevation angle in degrees by just taking the arc cosine of this. Now, notice this is a general formula. If you want to do this calculation on another planet, you want to figure out what the elevation is in Mars, you can just put the radius of Mars here and then use the radius from the centroid of Mars as r sub s. It's a generic mathematical formula that'll work for anything. But it is in 2 dimensions. Now, we're going to use this for our 3-dimensional formula. Our 3-dimensional formula is basically just going to add another step. Keep in mind, every 3-dimensional problem, if you slice it right, is a 2-dimensional problem. If I take a slicing plane that contains the radius, the centroid of the Earth station, and the satellite subpoint, I will splice that 3D problem, and it will look like, in a cross-section, it will look exactly like this. And so our pre-step, I'm not going to put it on just yet. I want to show you something else first. But our pre-step to the 3-dimensional problem is using our satellite subpoint and Earth station longitudes and latitudes to calculate gamma before we do this calculation. And then we move off into azimuth calculations. Okay, now, any good engineer trying to calculate an elevation angle will do one important test first. It's called the visibility test. They calculate gamma, and if gamma is less than or equal to the arc cosine of RE over RS, then the elevation angle is visible. It has not dropped below the horizons. Now, this isn't the final ultimate test on visibility, because there are a lot of other factors that play into visibility. Mountains could get in the way. Buildings and trees could get in the way and obstruct things. Your spacecraft could be optically visible, or at least line of sight visible, if you ray trace the path. But down on the horizon, there may be too much atmospheric attenuation in your signal to actually see the satellite, which would otherwise be audible if it was up overhead. So this is really just a geometrical visibility test. If I lived on a flat Earth out in the desert, is my satellite going to be above or below the horizon? If it's below the horizon, it doesn't matter how many mountains or what terrain you have, it's not going to be visible. And this is a good test to do, especially when you write code for your homework, because students get in trouble a lot of times on these assignments because they start to get nonsensical answers. So, for example, they'll graph elevation and azimuth. In this case, elevation goes from 0 to 90 degrees. 90 degrees is straight overhead. 0 is somewhere on the horizon. And then azimuth is 0 to 360 degrees, somewhere along here. And they'll give me a plot of a sky track of a satellite, where it's evolving over time in the sky, and where you would have to take your dish and track it around. And sometimes you'll see some crazy things like this. The satellite will do this. Boing, boing, boing. That is one messed up spacecraft, right? It would appear that this spacecraft is exerting a tremendous amount of station-keeping fuel at points like this, where it just decides to completely change directions for no reason. And again, over here. And what's actually happening is that they're using this formula over here, and they're getting some nonsense results because the visibility is dropped below the horizon, and they're getting MATLAB interpreting imaginary numbers on this graph or doing some crazy things. And so, in reality, what this is probably doing is the actual sky track is something like this. And if you put like a conditional statement for visibility in there, you'll get rid of all these points, which are actually somewhere below the horizon, giving nonsense results. So, yeah, always be wary when you show me code of sky tracks that just like suddenly bounce for no reason. Think about that. It takes a tremendous amount of rocket fuel to suddenly reverse like that. It's okay if there's like a little hook there, because that just means as the Earth's spinning and the satellite is doing its crazy inclined elliptical orbit, it just may be in some sort of peculiar place where it's accelerating and a little bit faster, then a little bit slower than the Earth's rotation at a given point, kind of loops around. That's permissible, but no points that bounce. Okay. Now, to extend this to 3 dimensions, there's a very simple formula. Calculation of that subtending gamma angle for 3D, the cosine of that gamma is equal to sine L sub s sine L sub e plus cosine L sub s. Got to look at my notes, make sure I don't mess this up. Too dangerous to do it from memory. This is too important of a formula. And there we have it. Now, what are the LS's and the LE's? Capital LS is the latitude of the satellite subpoint. Little ls is the longitude. And likewise, capital L sub e and little l sub e is the lat lon for the Earth station. And so, if you plug your latitude and longitude for satellite subpoint and Earth station in here, take the arc cosine of that, you'll get the gamma that we used in our original two-dimensional problem. Now, don't worry if the math is getting out of hand, because we've got to do azimuth, and it turns out azimuth is even tougher than elevation. I'll do an example, a numerical example with some real values to kind of show you how this all works by putting all the pieces together. Okay. Now, how do we do azimuth? This is also a two-step process. We need a helper azimuth variable, which by convention in this class we call alpha. And alpha, in this case, is the arc sine of the sine of your longitude of the Earth station minus the longitude of your satellite subpoint. Take the absolute value, then the sine, multiply that by the cosine of the latitude of your satellite subpoint divided by the sine of your gamma. So you really need to calculate elevation first, because we use that helper variable in this formula to simplify it. And you're not done yet. This gives you a number that kind of describes alpha, but you'll need to make some adjustments because of the ambiguity in 360 degrees in trying to make this calculation. First of all, when we measure alpha, what are we measuring? Or when we measure azimuth, what are we measuring? We're measuring the angle that you steer something along the horizon perpendicular to elevation in order to sight in your antenna. Where do we measure it from? Well, again, here's a case where we differ from mathematicians and engineers. We use the cartographer's convention for azimuth. And that's where north is 0 degrees and east is 90 degrees. So we are increasing in azimuth just clockwise, looking down from above. So if I do north, south, east, west, this is 0 degrees. Increasing azimuth increases in this direction clockwise until you get to 360 degrees where it repeats over here. That's, of course, very different than the Cartesian coordinate system, where we usually take this x-axis to be 0, and then we measure the angle of azimuth counterclockwise in that direction. Why that convention happened, I don't know. That's usually what cartographers and map people, geography people do. And so we point the dish with that type of terminology. Yes?
The east-west part, that's at the equator on the field there on the...
Oh, no. So this is actually looking down from above, right? And if you imagine this is what if you had an Earth station here and you looked at a compass, a good clarification of the diagram. If you just looked at a compass, you would have a north, a south, and an east and a west. And so the azimuth tells you where along that compass bearing should I actually point the dish antenna. So we need to make some correction factors to get the actual azimuth. And there's a second step, which is an adjustment step. And this is trickier than it looks. So put this table in your notes. The SSP, the satellite subpoint, is southwest of the Earth station. In other words, if I go to this diagram over here, this is my Earth station. I'm standing on the board. I'm looking down at somebody standing on the board or a dish mounted on the surface of the Earth like this. Southwest would mean that my satellite subpoint is somewhere in this quadrant. And if that's the case, then my actual azimuth is 180 degrees plus the alpha that I calculate with that formula. If instead the satellite subpoint is southeast of the Earth station, the azimuth is 180 degrees minus the alpha I calculate with that formula. If it is northwest of the Earth station, then my azimuth angle is 360 degrees minus the alpha that I calculate with that formula. And if it is finally northeast of the Earth station, the azimuth angle is actually just alpha, the value that I calculate with that formula. We're not done yet. We're not done yet. I have to make one more clarification before we apply these formulas. As if this conditional statement wasn't hard enough to code up, I have to be a little bit careful about how I actually calculate southwest, southeast, northeast, northwest. I had to figure out, is a satellite subpoint north or south, east or west of a given Earth station point? Well, the east and west calculation is very easy to make, right? And the reason why it's easy to make is because the longitude lines themselves bisect the Earth, right? If I pick a longitude line, it slices the Earth right down the middle into two equal halves of a sphere in ideal practice, right? It doesn't matter which longitude line I pick to do that. And so, really, that part's actually really easy. If the longitude of the satellite subpoint is less than, within 180 degrees less than the Earth station point, then I'm clearly east. And I'm either going to be this condition or this condition. If the satellite subpoint is greater than the Earth station longitude without wrapping around 180 degrees, then I'm clearly west of the Earth station. Okay, that's pretty simple to get. It gets a little more complicated. You can't do that same conditional test with pure latitude lines because, except for at the equator, the latitude lines do not bisect the Earth. They do not cut it into a perfect sphere. At the equator, if you have a North Pole and a South Pole, we're looking from the side. Here's the equator. Yeah, latitude 0 line slices the Earth in half. But if I'm up here at the poles, at a high latitude, like 80 degrees or 70 degrees, I just have a tiny little bit of Earth up here. And a huge amount of Earth right here. What I really need to determine whether something is in the northeast quadrant, the northwest quadrant, the southeast quadrant, the southwest quadrant, is a bisecting line test for this. Now that doesn't look like, what I'm really saying, if something is north, then it's going to be in this hemisphere. And if something is south, it's going to be in this hemisphere relative to my observation at the Earth station. You say, well, how is that possible? Look, you just drew a tremendous amount of trunk of the north part in the southern hemisphere. Well, imagine, if you will, if I'm sitting here on the Earth, let's say this is south, and this is north, and this is east, and this is west. Okay, if I want to figure out east and west, I draw a line this way. Let's say I have shot laser beams that could bend around the Earth from my fingers, and I line them perfectly with north and south. It would go around, and it come around, and it would mark this perfect set of hemispheres that I could divide into east and west. Now, if I did the same thing here, those laser beams would bend around the Earth, but they would do so in this fashion. They would start out like this, and then they would bend around the Earth and bisect it in half. And so even though the satellite subpoint might be down here close, it's clearly well below this line. The latitude may be very far below that line, but it's still north relative to that bisection test. So mathematically, how do we make that bisection test? That's the key. That's the key. And so north corresponds to the tangent of the latitude of the Earth station times the cosine of the differences between longitudes of the satellite subpoint and the Earth station. If that is less than the tangent of the latitude of the satellite subpoint, then you're north. If you reverse this condition, then you are, quote unquote, south. And all of these tests will work out. This can be a maddening error when you actually code up and calculate things, because especially if you pick a satellite that spends a lot of time near the equator, for low satellite subpoints and low Earth stations that are close to the equator, this test, just testing the outright latitude lines, actually is a pretty good estimate of whether the satellite subpoint is north or south of the Earth station. It gets a little bit hairy kind of around the equator, but you can run a SkyTrack simulation and it almost looks perfect. But as things start to get higher and higher in latitude, you'll get these kind of quirky looking SkyTracks where there'll be a little hitch in it. You'll say, well, where did that come from? It's probably an incorrect code that's not doing the north-south test correctly for the azimuth calculation and adjustment. So just be on the lookout for that. Okay. Now, this is the part where we get to do an example. What we're going to do is place an Earth station on the top of Van Leer and figure out where to point it to get to a geostationary Earth orbit satellite. So here's our formal problem statement. Earth station in Atlanta on the roof of Van Leer, which we just said was 33.7758 degrees latitude and negative 84.39738 degrees longitude. We have a geostationary Earth orbit satellite that is hovering synchronous with a sidereal day so that it never changes its satellite subpoint latitude. It's always at negative 105.0 degrees. That's, of course, 105 degrees west of Greenwich, England. So, what are the look angles? That would be in azimuth and elevation that this satellite, this Earth station should dial up on its antenna to point it towards a satellite. Okay, so first a couple supplemental pieces of information. We'll need these physical constants. RE, radius of the Earth, 6,378 kilometers. The RS is the value that we calculated earlier in class. We said this is a geostationary Earth orbit. We know that that's a circular orbit with a magic radius of 42,164 kilometers. And the satellite subpoint is 0 because it has to be 0. There can be no inclination for a geostationary Earth orbit satellite. And, of course, we said that it always hovers at the 105.0 degree longitude line. So, we've got our two latitudes and longitudes. Got our radii. Let's see if we can calculate this. So our step one, and I'm going to put the formulas down in the form that I put them in, that I entered in the numbers on the calculator. I'll give you the results. We won't work through all the numerical detail. You can double check it at home, but it'll be a nice template for your own problems just to verify that your codes are running or that you've typed in a formula in Mathematica or MATLAB correctly. Okay. Step one, calculate gamma. Gamma is equal to the arc cosine sine LS, sine LE, cosine LS, cosine LE, times the cosine of the difference between the longitude points. And if you do that for the numbers we've got there, I've got all my longitudes and latitudes. This turns out to be 38.4 degrees. Remember, that's just the subtending angle that's formed between the center of the Earth station, and the satellite subpoint. We still don't have elevation yet. To get that, that's step two. Calculate elevation. EL is equal to the arc cosine, just massaging the formula that I gave you on the previous page into a slightly different form. 1 plus RE over RS, quantity squared, minus 2 RE over RS, not squared, times cosine of gamma. If I do that, I plug the numbers into the Magic Professor calculator where everything is calculated ahead of time. That's my gamma. REs and RSs come from the problem statement, or what we inferred from the problem statement. That becomes 44.9 degrees. So about 45 degrees. So that's actually a really good result. That tells me from the horizon, how far do I have to jack up my antenna to point it so that it can see this satellite? Now I just got to calculate azimuth. So let's go ahead. Step 3. First I have to calculate the helper variable alpha. What formula do I use? Alpha equals arc sine absolute value LE minus LS, cosine capital LS over sine gamma. Again, you see this formula only depends on things that were given in the problem statement or inferred directly. We have all the information to calculate it, difference in longitudes, the latitude of the satellite subpoint, and that helper variable gamma. This gives me 34.1 degrees. And then finally, I make my adjustment. And for a simple calculation like this is actually pretty good. I have to make that adjustment. Is the satellite subpoint south, north, east, or west? Well, I'm in Atlanta. This is an equatorial satellite subpoint. And what's more, it's pretty close to my side of the world because it's a geostationary Earth orbit satellite that's serving North America, right? So without doing any fancy math, I could probably say that, well, clearly the satellite subpoint is south. And if Atlanta is at minus 84 and the longitude is at minus 105, this is also about 20 degrees west of us, where we're standing right now, more or less, in longitude. And so I would say this is southwest. So based on that contingency, I need to add 180 degrees to alpha, giving me 214.1 degrees of azimuth, as measured from the north, clockwise. So bear with me. Here's a little exercise. This may have no visual assistance to about half the people in the class. Some people are really good at 3D conceptualization. Other people kind of think of things differently and learn differently. But here, try to imagine it in your mind, because it makes a lot of sense when you do this, right? So I think, if I orient myself right, this is actually north in this building. I could get the compass out, but this is probably metal girders, and it might screw it up indoors anyway. But let's pretend for a second. This is north. Did I get it even remotely? Have you sighted this in? Okay, good. You have a good sense of direction. Thank you. So that means north, west, east. If we just kind of visualize it in our mind, we're up on the Earth at about 34 degrees latitude, and the geostationary Earth orbit satellite is kind of shot out from the equator multiple radii of the Earth away. And so if that's north and that's south, I figure I'd have to raise my dish up here and then tilt it over there somewhere. Now, without even doing any calculations, right? And let's see, does that jive with what we've said? We've got 214 degrees, which means I start north, I go all the way around to 180 degrees, and then I got to go 34 degrees more, which would be about there. And then I got to jack up to about 45 degrees. That's my geostationary Earth orbit satellite right there. I could draw a laser beam, and I'd probably knock something out of orbit, right? Burn it up, knock out somebody's television service or some critical communications infrastructure. And so that's at least a hand-waving, literally, explanation for or verification of these look angle formulas. They do seem to geometrically make sense based on this intuitive, based in Atlanta, geostationary Earth orbit example. So any questions before we continue on with look angles? Yeah?
So when we're putting this up, should we also put in like the visibility test at some point?
It probably would be a good idea. And that would be a sort of step 1.5. Just do a quick test and say, am I going to get nonsense out? Should I even continue this calculation? That's a very good question. Leave it to the aerospace engineer to ask a good question like that. Any other questions? Now, okay. Now keep in mind that the sky track that you make on the Earth from a relative vantage point on the Earth really says a lot about the application for the satellite. We haven't talked about that much about some of these crazier different types of orbits, but if you add elliptical orbits and inclination and change periods around, you can make some really interesting orbits that accomplish some interesting things from a coverage point of view or a Skytrack point of view from a vantage point on the Earth. I'm going to give you a couple examples now of that. In fact, I'm going to give you two old Russian orbits that the Russians developed in the early days of the space race. And they're very interesting because they have some interesting properties and they accomplish some really interesting things. So first of all, the first orbit that we'll talk about is the Molniya orbit. So what are the specs of the Molniya orbit? Okay. Period of 1/2 of a sidereal day. So it will repeat itself exactly 2 times during the course of 1 sidereal day. Let's see. Next one. Highly eccentric. The perigee, the lowest point of the Earth of the orbit, is essentially a low Earth orbit. The high point, in order to get a period of 12 hours roughly, the apogee is actually somewhere in medium Earth orbit, somewhere very high. And the other piece of information that you need to know is that this is inclined by 63 degrees. So if I were to sketch this orbit, here's the Earth, here's the equatorial plane, the North Pole and the South Pole, at least by geography. Not the magnetic North Pole or the South Pole, slightly different than the axis of rotation. But this orbit would look something like this. It would be the plane of this orbit. Normally it would be in the equatorial plane, but they've inclined it by a factor of 63 degrees. Why 63 degrees? Well, it turns out that based on the aberrations in the shape of the Earth, this is sort of a minimum in station-keeping corrections that you need to do for a spacecraft in this kind of inclined orbit. The aberrations all kind of cancel them out in this magical 63-degree inclined plane. So you don't have to use as much station-keeping fuel. I don't know exactly how much it saves you, but it's enough to actually want to put satellites in that type of orbit. Now, I've used the term Skytrack. The first thing when you go to sketch out an orbit, it's usually good to talk about the ground track. And that's basically the path that the satellite subpoint would make as it goes around the Earth in an orbit. So here you are going to be subjected to Professor Durgin's notorious speed cartography. Ready? Ready? I'm going to draw the world in 5 seconds. Australia, Africa, Asia, North America, South America. Did I leave out anything? Oh, Antarctica. Okay. Greenland. Oh, yes, of course. Let's not forget that. Let's make this as accurate as possible. Thank you. Thank you. Okay, so here we are. And where are the Russians? Clearly over here. Now, half a world away, right? Half a sidereal day away. Now, what would the ground track of this orbit look like as it went over the course of 2 days? Well, or as it went over the course of 2 periods, which would equal 1 sidereal day. Remember, because it's exactly a half a sidereal day, this ground track should repeat itself every day. It'll loop back in on itself. Because remember, all the while these orbits are evolving, the Earth is rotating underneath of them. So computing a ground track is no small task, because you've got to factor in the rotation of the Earth, subtract it out for every increment that you advance your orbital calculation. And so what we find for the inclined Molniya orbit, we have to apply a little bit of Kepler's law, too. When it's in the southern hemisphere, at perigee, it's moving a lot faster than at apogee when it's in the northern hemisphere. So it's not going to look symmetrical here. I'm going to draw on the board what it looks like and see if you can kind of map what's going on without doing a bunch of equations, a good conceptual exercise. Remember, it's got to repeat twice in a day, and it's got to loop back in on itself at the end of a day. And it's got to, okay, so let's start. Let's say it's at the equator, and it's coming down the backside of the planet, whipping around the planet at perigee, traveling very quickly. It's going to look like this. The ground track, the satellite subpoint. And then it gets up here, and it's going to start slowing down. And in fact, it could even kind of dip backwards a little, because at this time, the Earth's rotation is sort of catching up with it. It's slowing down. It's not making as much forward progress. And it's going to go really high, because this is very eccentric. It's being thrown very high up into the sky at a high satellite subpoint, high latitude satellite subpoint. It's going to meander there for a little bit, and then all of a sudden it's going to start falling back to the Earth. It's going to start accelerating. It's going to get faster than the rotation of the Earth. It's going to whip around the backside of the planet. It's going to pop up over here. And it's going to do the same thing, lazily arc in the sky, and then whip around the back side of the planet. And then it does this every single day. Look at that. Spy on America, report to Russia. Spy on America, report to Russia. See, you can do a lot with a clever orbit. It was very obvious what this orbit was intended to do, right? Very clever. Now, it turns out that the Russians developed a number of really clever orbits like this. And we shamelessly stole some of them for commercial purposes later on in life, right? So, for example, there's another similar orbit called a Tundra Orbit. A Tundra Orbit. This is a Molniya orbit. The Tundra Orbit is similar to the Molniya, except it's a period of 1 sidereal day. But otherwise, it is eccentric, has a different eccentricity. And it is also inclined at the exact same angle, 63 degrees, again, to minimize station-keeping operations. It also happens to be that when you incline an elliptical orbit like that, the apogee spends a lot of time in the northern hemisphere. And if you're in the northern states of the United States, or you're in Russia, that's a good thing. You don't get very good coverage from stuff on the equator all the time. And of course, some American companies realized that too. So they took this Tundra orbit, and there was a company. So here's the equator. Let's do some speed cartography again. North America, South America, Europe, Africa, Asia, Australia. There was a satellite called company, Sirius Satellite Radio. They launched 3 satellites that were essentially in the same Tundra orbit around the U.S., around the planet. 1 sidereal day, inclined. The ground track would look like this. It would actually look kind of like a bowling pin. Remember, It's a geosynchronous orbit, not geostationary, geosynchronous, which means the net movement during the course of a day, the satellite's going to come right back to where it is, and on average, it's going to stay in sync with the Earth. Because it's inclined and it's elliptical, sometimes it's going to be going faster, sometimes it's going to be slower, but it's going to pretty much stay in the same median longitude. And that's pretty much what it looks like. What's going to happen when the satellite is whipping around the backside of the planet at perigee, we find that it's going to accelerate and go faster than the speed, the rotation of the Earth. So the satellite at some point is kind of going to get out in front. And then when it whips around to the northern side and gets to the higher apogee, it'll slow down. And it makes a sort of figure eight. And the figure eight belies the fact that most of the time the satellite is spending up here in the northern hemisphere by Kepler's second law, right? Equal areas are swept out at equal time. It's sweeping out larger radii, but the same amount of area, so it's just not as advancing as much. And then here it's kind of whipping around the backside of the planet. And so if you carefully put 3 satellites in that constellation, one of them is always slowly hovering up here at the ground track, which means it's going to be roughly right overhead from North America, and it's going to give you really good coverage. Now, contrast that to what once was XM radio. Their strategy was to put 2 geostationary Earth orbit satellites into orbit. One on the east side of the country called Rock, and the other one on the west side of the country called Roll. And the idea was they would broadcast to different sides of North America. And if you had a little mobile unit with it was around 2 gigahertz was the band, you could listen to the radio wherever you were. And it was a great system, especially if you lived in Florida, in Georgia, in Arizona, in Texas. It got a little dicey when you used XM radio up in Maine or Seattle, where the look angle and elevation would start to dip down because this was an equatorial satellite, and you might run into mountains or trees or buildings that would easily occlude the satellite link. And so the 2 companies merged. I think Sirius is the one with the name left, merged. And for a while, at least, they kept both systems going because they served 2 different purposes, right? If you wanted a mobile link, the Sirius satellite network was the way to go because you always had a satellite overhead that was unobstructed. On the other hand, if you were a shopping mall and you just wanted really reliable coverage and you had the luxury of piping in your satellite radio by hammering a little dish or a directional antenna onto your top of your building and just pointing it, cementing it in, not having to change it, then the geostationary Earth orbit approach was the best. You got the best link margins because you got to steer an antenna in that direction. So it didn't matter if it was a little bit on the horizon. So you can see that choosing which orbit, you can choose a radically different orbit for the same application, and it kind of changes who you wind up servicing as a communications customer, with some overlap, of course. But there's a lot of design freedom in picking these shapes of orbits. Any questions? Any questions? Okay. Let me give you an example. I'm going to go to the document camera here instead of doing my speed cartography. And I'll draw on some maps just to give you a better feel for this. This is ripped. This document is ripped right off the Did I turn it on? Yeah, we got it on now. See, can we get the document camera up? Oh, I saw it. It flashed. It's coming. It wants to. I wonder, oh, I bet you it's, this thing was bent. Sorry about that. Yeah, there we go. Perfect. Here's a picture of a Tundra Orbit, kind of like I drew it on the board. You'll see every day it makes that trace. And there's kind of a picture on space of what it looks like. And of course, here is the Tundra Orbit. Again, looks like a teardrop most of the time, even though it doesn't look like it in terms of path length. But on the ground track, most of the time, the satellite is up here, slowly slowing down at apogee, and then speeding up to go on the backside of the planet. Now, and here's a little mapping. You see that the Tundra Orbit actually isn't all that eccentric. So here's the center. Here's where the Earth would be. The Earth would be about this big. And because it's one sidereal day, the mean radius is pretty close to what a geostationary Earth orbit satellite would be. It's just a little short over here, a little long over here. So it'll speed up through this path here, slow down here. What would that look like in terms of a look angles from a North American vantage point? So I have two examples plotted up here. Let's see. One, this is a sky track from Atlanta. I used the Sirius coordinates from Atlanta. And so I've got 150. This graph is rectangular. It goes from 150 to close to 360. So this would be north, and this would be like a little bit southeast all the way over here. So you span a little more than 180 degrees in this plot. And then the y-axis goes from 0 to 90 degrees. In your plots that you are doing for your homework, there's multiple ways to plot these things. Doing a box rectangular plot like this is perfectly acceptable if you'd like to do that. And if you do that, what you see is that the satellite pops up above the horizon, hangs around almost overhead at very high elevation, and then pops right back down. So it's very good for covering the Earth. Now over here is the same plot, except I've plotted it in a polar fashion. What I've done is I've plotted azimuth, 0 to 360, in this typical polar dimension of angle. And then from distance, I've plotted the cosine of elevation. So cosine is 0 on the horizon is over here. Cosine of 90 degrees is straight up here, like here. And this is nice because it gives you a sort of fisheye perspective of the sky track. If you were laying on the ground looking straight up in the sky, this is roughly what you'd see. This rim would be the horizon, and the satellite would come up here, kind of dance around, and then fall back below the horizon. So they're really the same plots. You can plot your sky track however you like, this one or that one. I myself kind of like this one because it's a little more accurate. You can kind of envision yourself laying on the ground and looking up at the sky. So that's the satellite and how it would look from Atlanta, Georgia. This is the plot how it would look from Bangor, Maine. Now you're way up in latitude, right close to 50-something. And you can see that because of the high inclination, the satellite still jumps up and spends a lot of time very high in the sky relative to a main observer, and then falls back down. So here, on the fisheye plot, that looks like this. Satellite kind of spirals up, gets close to the very zenith overhead, and then kind of loops back down. And this is probably a good 12 plus hours it spends on this section right here. So you get good coverage. You drop one or two more satellites in this same orbit, and as one falls off, the other one comes back in and continues to cover. Okay, any questions about look angles or some of these orbits that we talked about? None? This is the class that always has perfect understanding. What a great class. Okay. Oh, good, good.
Still operate?
Yes. I think, because I don't just subscribe to any of this. You can either study communications or you can use it. You can't do both. There's not enough time in the world. Right? Who here subscribes to a satellite radio? Maybe parents subscribe to a satellite radio station.
Well, I got a new car and it's in there, so.
Yeah.
Oh, yeah. Which one is it? Is it Sirius?
I think it's called Sirius XM.
Sirius XM. Oh, they combined the name. Yeah. I don't know if they still service both satellites still. They used to keep both of them active. I have to look that up. Any other questions? Yeah.
So basically, these orbits are achieved by putting the satellite in a particular type of orbit and getting the spin of the Earth to rotate and making it where it draws this.
That's right. That's right. So you got to put it in the right orbit with the right eccentricity, the right period, and then you also have to do it with the right inclination, and you have to time it right too, so that if you're doing this Sirius Tundra orbit, your median longitude is somewhere centered on North America, and you didn't accidentally put it over the Pacific Ocean or the Atlantic Ocean. So there's a lot to get right in the timing of when you launch and how you launch it, and what kind of final coordinates you give its velocity and position.